Thank you very much. Yes, I'm going to be talking today about some work I've been doing as part of my PhD alongside Mark Purnell at Leicester with Julia Fahlke from Berlin and Katharina Bastl from Vienna. We're looking at dietary evolution in Archaeocete whales using three-dimensional tooth microtextures. And I feel that this talk's quite fitting for this conference, given that we're very near the birthplace of Ted Hughes, who wrote a very nice short story for children, admittedly, How the Whale Became, which you should all give a read if you haven't already. So, what question are we trying to answer? Well, is the origin of whales linked to long-term dietary trends from terrestrial to obligate aquatic feeding? And what we're really saying here is there a smooth trend in diet as the whale ancestors move into semi-aquatic habitats and into fully marine habitats? This is an iconic ecological and evolutionary question, and morphological analysis has often suggested this smooth transition, but this has been questioned recently using gross tooth wear morphology. The Archaeocete whales themselves, as I'm sure most of you know, are a stem group of the cetaceans that were around between the Eocene and the Oligocene, and represent this direct transition from their closest relatives, which are Archaeodactyls, specifically the hippopotamids, through, which are terrestrial herbivores, through semi-aquatic forms and onto fully marine forms, which are the precursors to the modern mysticetes and odontocetes. Alongside this, we obviously see a great range of morphological changes in these animals, from elongation of the body pattern, especially the skull, elongation of the vertebrae, and the tail, the development of tail flukes. And alongside this, we get a change in dentition through evolution, with the move away from the heterodont dentition that you get in Archaeodactyls to a more polydont dentition in the Archaeocete whales, with an increase through the evolution of these animals of the proportion of homodont-like teeth in the jaw, which are obviously the homodont teeth are very similar to the modern odontocete teeth. What's really interesting is that while the front teeth of the animals are very similar to those of modern odontocetes, the rear teeth bear a much greater similarity to modern pinnipeds with this multi-cusped triangular dentition. So how can we test this ecological transition in Archaeocete whales? Well, we could use functional morphology. However, previous microware studies have suggested that diet is sometimes independent of dental morphology, and so therefore we may be testing something where form doesn't necessarily follow function. Isotope analysis could be used, and this has been used to look at the move through from freshwater to salt water in these animals. However, while it can test trophic levels within an ecosystem, it shouldn't really be used to compare different ecosystems spanning millions of years, which is the situation we have with Archaeocete whales. And this leads us on to dental microtexture analysis. And this is a three-dimensional approach which objectively looks at diet based on operator-independent surface texture parameters and is not affected by time or morphological bias. However, before we can even begin to look at the Archaeocete whales, we have to develop a set of proxies from modern diets to compare these Archaeocete whales to. So our first question has to be, does dental microtexture vary with diet in modern aquatic mammals? Because if it doesn't, we've got nothing to compare these Archaeocete whales to, and obviously we can't draw any real conclusions from them. So to test this, we've selected three groups of pinnipeds: the ring seal and the grey seal, which are primarily fish eaters; the harbour seal and the harp seal, which have a large crustacean element to their diet; and the northern fur seal and the stellar sea lion, which have a large cephalopod element to their diet. We've also included three species of odontocetes: the Atlantic white-sided dolphin, the bottlenose dolphin, and the killer whale, which are all fish eaters. This data comes from stomach contents and isotope analysis, and this is a specific pod of killer whales that are suggested to be only eating fish. So we can collect data from these modern aquatic mammals. We take one tooth per individual from as close to the same location in the jaw as is physically possible, which isn't easy given that you've got varying dentition between the animals. And we select a 100 by 140 micron area to collect three-dimensional data from. We then remove large wavelength information from the data, which is the gross tooth morphology and the waviness in the texture, to leave us just with the roughness of the surface. And this is done using polynomial and spline filters. And then we calculate 22 parameters based on an international standards organization set of texture parameters, which come in 6 categories based on direct surface measurements. And these can measure anything from the absolute heights of peaks to the absolute depth of valleys, or ratios of material in different areas of the surface, or ratios of void in different areas of the surface. So then once we've got our data, we can carry out statistical analysis on it. The log data for all of our dietary groups was normally distributed, so we use that going forwards. And using ANOVAs, 8 out of 22 parameters showed significant differences between the pinniped dietary groups. If we look at Tukey tests, 5 of these were differentiating the fish eaters from the cephalopod eaters, 2 were separating the cephalopod eaters from the fish eaters, and 1 was separating the cephalopod eaters from the crustacean eaters. We can then take this and take these 8 parameters and carry out a principal components analysis to create a dietary shape space, as it were. And we find that we can separate the cephalopods and the fish eaters, to some extent along principal component 2, but not along principal component 1, and both of these separate neatly from the crustacean eaters along principal component 1. And we would suggest, therefore, that principal component 1 seems to be quite a good indicator of the crunchiness of food items in the diet. I wouldn't like to use the word hard food items, but crunchy food items we'll go with. And then we can compare this to the odontocete fish eaters that we have, and if we test them against the pinniped fish eaters, only 1 out of 22 parameters show significant differences, which is what you'd expect by random chance, suggesting that what we're seeing is not a taxonomic artifact of diet, but is actually a dietary signal. And if you plot these into the same principal component space, they overlap quite nicely with the fish eaters. So this allows us to expand our fish-eating dietary space and give us a range against which we can go back and compare our Archaeocete whales. And so the answer to our halfway question is yes, tooth microtextures do vary with diet in modern aquatic mammals, and we can therefore use this to compare to Archaeocete tooth microtextures. So we go back to the Archaeocete whales and we do the same sort of thing. We select a number of species. We have 5 basilosaurs from 3 different species, 6 procesetids from 3 from known species to 3 unidentified procesetids, and a single Pachycetus in our specimen. We then collect data in the same way, a single tooth per individual from as close to the same location as is physically possible, and then a 100 by 140 micron sample area from which we collect 3D data and the 22 roughness parameters. We can then take the 8 roughness parameters that separated the pinniped dietary groups and plot them into the same dietary space. And we find they fall like this. And I'm going to go through this carefully. There's several inferences that we can immediately draw from this. Firstly, Pachycetus falls neatly within the fish eaters with a very low level of crunchy food items in the diet. The procesetids fall into 2 groups. One, along with a basilosaur, falling between the fish eaters and the cephalopod eaters, suggesting that their diet was a mixture of these things. And one, including Caesarocetus, which has been suggested to eat crunchier or harder food items, way beyond the range that we see for the pinniped generalists, suggesting even crunchier food items in the diet. Similarly for the basilosaurs, they range way beyond what we see in the pinnipeds, but some do overlap, and this varies greatly even within single species. So all the bees are Basilosaurus, but some are eating similar things to the pinniped crustacean eaters, and some are eating things with much crunchier elements in the diet. So what we see here is a transition along principal component 1 with diet, with crunchiness of food items in the diet. So we can go back to our original question now, which is there a smooth dietary transition through the semi-aquatic to the fully marine forms of Archaeocete whales? We can do this by ranking the branching order of these animals. Unfortunately, the processes are all a polytomy at the moment, so they've all been given a 2, but we go from our most primitive animal, which is Pachycetus, given a 1, up to the most derived, given a 5. We can then plot this rank against our principal component 1 scores to determine any correlation between the 2. And we find this result, that there is a very low correlation with no significance between taxonomic rank and principal component 1, which is our dietary proxy for crunchiness of food items in the diet. This tells us that the answer to our initial question is no. It's not a smooth transition from through the semi-aquatic forms out to the fully marine forms, and there's a much more complex pattern in there of varying diet even within each group. So obviously that's the main conclusion we can draw from this, but the other conclusions we can draw are that we are able, and this is the first time this has been done, to separate marine mammals using tooth microtextures into dietary groups. Obviously not so well between the fish eaters and the cephalopods. You would expect some overlap given the similarity in sort of the types of food, as it were. We can also say that it is likely that Pachycetus was a fish eater, and that the protocetids fall into two groups depending on the species. One that ate a mixture of fish and cephalopods, and one that ate much crunchier food items. And the Basilosaurids all seem to have some element of crunchy food items in their diet, but this varies within species quite drastically. So we'd like to thank the following institutions for access to specimens, and thank you all very much for listening.